Let's talk about dividing polynomials. This is section 2.4. We could also call it factoring polynomials because, as we shall see, it amounts to the same thing. First, let's talk about division in the natural numbers. Okay, so here we have a quotient on the left. 32 divided by 8 is equal to 4. Now, I wouldn't even know the term dividend for numerator unless it had been mentioned in the book. But divisor, the thing that we're dividing by, and quotient, those are very important words, even to me. So those are the ones that I focus on. Now, suppose that we divide 35 by 8, knowing that 8 does not go into 35 directly, or completely. So we have a quotient that has a fraction added to it. And if we say that 35 is equal to 8 times 4 plus 3, we're actually saying the very same thing that we said with 35 divided by 8 is 4 3/8. We have our number on the left. We have right here the divisor and the quotient, and in this case we have a remainder. Now, notice that the remainder is always less than the divisor. If it weren't, it would not be a remainder. We'd have had another factor of 8 in the original thing. And if we like, we can look at this first division that we did of these two numbers as the quotient plus the remainder divided by the divisor. Okay, so now let's extend this idea to division in polynomials. We can think of polynomials as another entire space of numbers similar to the natural numbers or the reals or what have you. We have the definition of a polynomial with which we're already familiar. Important things here: one, the exponents are strictly integers, positive integers or 0. And the leading coefficient must not be equal to 0. Okay, now here I divide one polynomial by another. This is very familiar because we already can see when we look at this the factors of that polynomial. So, the reason that I would like to emphasize means that the first thing means the second is, if you'll recall from probably the first day of the semester, when we talked about why division by 0 is undefined. It has to do with the fact that division is defined in terms of multiplication. So here we see a simple example of that. This division is defined by this multiplication. So dividing and finding factors of a product are in fact the same thing. In this case, I did not have a remainder. I don't know, is that a good thing or a bad thing? Next, long division. Again, we're going to look at it in both the natural numbers and then in polynomials. So, I need to do long division when I have two numbers that are not among the elementary facts that I know, as in this case. So, 12 goes first into the first two digits. I write them down, I subtract. This is what I get, and I carefully bring the 4 down, etc., etc. So, this quotient here, with this divisor, this business means that 504 is in fact our divisor times the quotient plus the remainder. Now, take care that you align these things carefully. I hope you can see the little pink dots there. Why do you do that? Well, neatness counts. We don't want to have things messed up, get our tens and our ones and our hundreds mixed up for no good reason. Second example, by looking at the 12 here and the 5 there, we know we're going to have a remainder here, don't we? And there it is. So, rewriting this division example as a multiplication, there we have our number is equal to the divisor times the quotient plus a remainder. And the remainder is definitely less than the divisor. This double arrowhead here means strictly less than. So the remainder is always less than the divisor. Not all the way less. The remainder can't be smaller than 0. Okay, long division in polynomials. I wonder if you knew you could do this. I didn't. But we can. We're going to use this as though this were hundreds and this were tens and this were ones. So the first thing I need to do is to figure out, looking only at the first terms of the two polynomials, how many times does x go into x squared? And it goes in there x times. So with my careful alignment, I put this x over that x because they both have the same exponent, which is 1. I multiply z. I subtract, and this is what I get. I'm always going to have 0 in the first column here. And then I bring down the next column and look at the first two terms of the polynomials that I have and do the same thing. X goes into 5x 5 times. I multiply and I subtract, and behold, I have a remainder of 0, which is no surprise because when we look at x squared plus 8x plus 15, we can hardly help seeing it, can we, as x plus 3 times x plus 5. Notice again that I am carefully aligning everything. Failure to align leads to serious trouble. Okay, so my long division has yielded this result. Number over divisor is equal to quotient, and in other words, the polynomial that we started with is equal to the product of these two factors, and in this case the divisor times the quotient. So, you write it either way, it means exactly the same thing. Here's a long division in the space of polynomials, and I see this 3 and I see this 7, and I think I am bound to have a remainder. So I want you to stop the video here and try it. If you have your video expanded to the full screen, you can just hit the space bar and it'll pause for you. There's my remainder of 4. So I can write this either of two ways. I can write it as though the remainder were a fraction, the way that we did with that 35 divided by 8. And here it looks the same thing. I have the remainder over the divisor, just as I had 3 over 8 in the previous case. And the degree of the remainder is absolutely strictly less than the degree of the divisor. In this case, it's a simple divisor of degree 1, but the fact remains. Then, I can also write it this way, as this product is equal to this divisor times that quotient plus a remainder. Okay, now observe the remainder doesn't look the same in these two cases. Here I write it as a polynomial, which is a constant function, all by itself. In this case, it was that polynomial over the original divisor, just as this was over the original divisor. Okay, a longer example. What will be the degree of the quotient? Well, we see that the original polynomial is of degree 3, the thing going into it is of degree 1, my quotient has to have degree 2, so that I have two factors that multiply together to make something of degree 3. Okay, you work this out, please. And here's how this long division works out, in this case without a remainder. Man, look at that beautiful alignment. Here's another one to try. Now we have a remainder. I chose this one because it had some negative numbers here. This can get kind of tricky when you are subtracting, because we have to change the signs. In any case, our result is the same. We have the divisor times the quotient plus the remainder. Now, observe that unlike the previous cases, we don't have x to the fourth something, x to the third, x squared, x, and then finally a constant term. So when we do the long division, we have to carefully put in those columns. That's so we can keep everything aligned. So kindly pause the video here and try it your own self. Notice when I subtract the first, I don't know, I guess you'd call that a subproduct here, the sign changes. And then I bring down the zeroth, I'm subtracting this negative 3x cubed from the 0x cubed and bringing down another column of 0. I changed signs and added. Some students say that to themselves. I'm not crazy about that. I want to see the original. At any rate, here's my result. So x minus 3 goes into x to the fourth minus 81 without a remainder. Now, some of you may have looked at this and said to yourselves, aha, there's a quadratic form there. Yes, there is. And if we exploit that quadratic form, thinking of it as something squared minus something else squared, why? Look at that. And then we can factor it a little bit further. So we can write our quotient as you see it on the right, but as we see it on the right here, that's another special form that we remember all the way from last week, and it calls for complex roots. Now, apropos of those complex roots, if we had thought about this original dividend, pardon the expression, about its graph, we'd have known using transformations that there are only two real roots to begin with. When we factor it, we do see that we have those two real roots. If there are only two of them, yet it's a polynomial of degree 4, then we have to have two more roots that are complex. Because why? Because anything with fourth degree, we have to have 4 zeros. Okay, here's another one. Now, observe in the divisor in this case, I don't have a term for x to the power 1. So, here's what I do. As usual, I look at how the first two terms are related. They're related by this 6x squared. And I write that down, and folks, I leave a gap. So that when I subtract, I'm subtracting 0 from 9x cubed, and I have 9x cubed still. And I put down the term that I can't see, that 0x, because I'm going to need it with the next bit. And so here you can see that I've brought down zeros that I couldn't see in the first place, and I have carefully left gaps. And what do I have? I have a remainder. The degree of my remainder now is linear. We didn't see that before. All of our degrees before were constants. And the degree of the remainder is less than the degree of the original divisor. And that's the end of this segment.